We're at lecture 11, and in the last lecture what we did was look at simultaneous observables and commutators. In the next lecture I'm going to get to uncertainty principle, and so what I like to do in the lecture in between is actually look a little bit at the statistics of uncertainty. Let me bring some slides up. The main reason why I like to do this here is that in the past, having taught this course, what happens is that I hit a small problem, which is that there's a gap in the maths. And the gap in the maths arises because essentially statistics is the ugly cousin of mathematics. So you come into a university, it doesn't really matter what university it is, and you'll look in the first year maths course guide and you'll see something along the lines of, although Maths 1 contains an introduction to the theory of statistics, it is primarily concerned with the study of two broad areas, linear algebra and calculus. Now, linear algebra and calculus are important, but what happens is the primarily concerned makes them quite big, and of course there's a limited amount of time, so that although becomes rather small. And then what tends to happen is that students come into the second year course in quantum mechanics, they haven't done a proper course on statistics yet, because often that happens later in second year maths or beyond that, if they take it at all. And so it means they often come into the course with little more in statistics than an average, and often not a very good understanding of standard deviation and the concept of root mean square. And so what I like to do at this point between getting commutators and getting the uncertainty principle is actually to make sure we're really clear on what uncertainty means from a statistical perspective. And it's a concept that's actually really helpful for your lab programs and so forth as well. So it's kind of nice to just trip back over it briefly and have another look. So the way I'm going to do this lecture, I'm going to break it into two halves. In the first half, I'm just going to look at the idea of root mean square and standard deviation, just to get really locked down on what that is. And then in the second half, what I'm going to need to do for lecture 12 is have a concept in place where I can basically take a statistical distribution and shift it, and know that the uncertainty that I would get for that distribution at some non-zero mean still is the same, even though I've shifted it to a zero mean. And I need something similar for my commutators as well, okay? And so I'm going to prove both of those things in the second half of today's lecture. So we need to be very certain about what we mean by uncertainty if we want to quantify it. And so the best way to start thinking about this is to come back to the idea of expectation value that we had way back in lecture 4 and 5 of the course. Back there, what we did was defined it as the probability weighted average of the observable outcomes. And when we just had our sort of electron spin system where there's only two observable outcomes, spin up and spin down, it was quite a simple concept, right? You have 50% probability of up, 50% probability of down, half times plus 1 plus a half times minus 1 is 0. And so this expectation value kind of told us what we should expect for our measurement. In the lecture before last, what we did was we went from this sort of two observable spin system to an infinite observable system where we basically have a particle on a 1D line with a position and a momentum, okay? And what we decided there to do was basically treat every position x as an eigenvalue, and every position x has a probability that's connected to a complex valued function that we call the wave function, okay? So imagine we have a particle sitting at some position x. What we would find is the probability, if we look, of finding it somewhere, you know, way out in high x is very, very low. Down on the other side, it would be very, very low. If we're looking very close to the particle, it might be quite high. If we look a little bit further away, it'll be a little bit lower. If we look a bit closer, it'll be a little bit higher, okay? And so at that point, it makes sense to start considering this as something like a statistical distribution rather than just a number. So once we have a statistical distribution, it starts to become meaningful to think about what the width is. Because if you imagine having our particle here, right? Imagine the probability stays very, very low and only starts to become significant very close to it. Then if you do a measurement of the particle, you're going to get something very close to the particle when you do that measurement. And so your uncertainty on where that particle is kind of small. In contrast, if you have a probability that sort of starts to become finite from a long way away and sort of gradually gets up here, if you do an observation, there's a probability that you'll find the particle is over here, even though it's here, right? And so now that we've got this broader probability distribution, our certainty on where the particle is is not as good. Our uncertainty is larger in this. What we need to do is kind of come up with a mathematically rigorous definition for what the width of that distribution is. And normally we take this from the starting point of treating that distribution as Gaussian and take it as the standard deviation. Okay, so if we're going to get to standard deviation, we need a concept, an important concept that's called root mean square. Okay, so what we can do in here is have the average. And imagine what we want to do is get some idea of what the typical separation of some observation is from that average. If we considered taking an average there, what we would do is have a whole pile of different numbers that are on the positive side and a whole pile of different numbers that are on the negative side. And we could look at a displacement between the observation that we make, which might be at some position x, and the mean of the distribution, which we'll call mu, which is just the Greek letter for m, okay? And so if we started to average this, we would have a positive number, a negative number, a positive number, a negative number. And for a symmetric distribution, every number that's on the positive will have a corresponding number on the negative. And so ultimately you'll find out that the average discrepancy away from that mean is 0 because all of the signs cancel out, okay? So one thing that we tend to do a lot when we're looking at statistical distributions is a thing called root mean square. So the idea is that we take all of the numbers that we're wanting to average, we square them all, then we take the mean, then we take the square root again, okay? What that does is for a positive number, when you take the square, it stays positive. You then take the average, then you take the square root, and you get back a positive number. If you go to the negative side, you take the square of a negative number is now a positive number. You take the mean, and then you take the square root of that mean, and that will give you back another positive number, okay? So essentially what we're doing is we're taking every number that's on the other side of the distribution and transplanting it onto the positive side so that when we take that average, the sign doesn't cancel out the answer, okay? Really important concept all the way through physics of root mean square, and it's basically central to what we do with taking the standard deviation. So usually what we can do in here, and I'll need some paper, is have two definitions for statistical width or distribution width. The first is something that we call the variance. It's usually written as var of x, and it's really just the average of what our particular position is, x minus the average mu squared. And so really what we're doing there is just taking the square mean displacement away from what we're looking for. The one that we actually tend to prefer, because it's actually a more representative measure of what the actual real width of the distribution is called sigma for standard deviation. And it's basically the square root of this variance x. So it would be square root of the average of x minus mu squared, like so. And so you can see in there, if you work from the thing in, on the inside of the brackets, x minus mu, which is really just the discrepancy between what you measure and the mean of the distribution, you square it first. The angle brackets are taking an average, and then the square root on the top is taking the root. So it's root mean square of whatever's on the inside, okay? All right, so there's one useful transformation I want to make in here, which is basically to get from our definition of the standard deviation to a slightly different definition of the standard deviation that essentially is the square root of the difference between two averages, okay? Okay, so we can start by writing our standard deviation here, x minus mu squared mean root. And then the first step here is basically just to expand these brackets in the center. So we've got x squared minus 2 mu x plus mu squared. And then the next step, what we can do is we use our knowledge that the average of a sum is equal to the sum of the averages. Okay, if you don't trust me on that one, I'll let you check it yourself because it's actually a fairly quick thing to do. So this will be square root of average of x squared minus, let's make it plus average of minus 2 mu x plus average of mu squared in here. Okay, so at this point, what we can do is use the fact that we know that mu is just a number, right? So the average of a number is just a number, right? It's sort of meaningless to have the average of an average. It's just already the average. And as you know, if you have, if you're taking an average of something times every single number, you can pull that number out of the front of the average. So what we can do here is write this as the square root of x squared minus 2 mu average of x plus mu squared on the end there. Okay, all these little things like pulling numbers outside of averages and average of a sum being sum of an average are pretty quickly checkable. Then the next step in here is that we know that this term in here, average of x, is just mu, right? Because we're looking at a distribution in x, and so that is just going to be the average position anyway. So what we can do is here go average of x squared minus 2 mu plus mu squared just here. And of course, this mu in the middle here is really just mu squared. And so we can write this as x squared average minus mu squared as a result here. Okay, so basically we're just cleaning up this minus 2 mu squared and the mu squared on the end. And of course we know that mu squared is just the average of x. So we can make that jump back again and write this thing in a form that looks like this. Average of x squared minus average squared. And so that gets us to our final result just here, which is we can write the standard deviation as the square root of the difference between the average of the square of x minus the square of the average of x. Okay, it's a really handy way to keep in mind for having sort of a definition for standard deviation, and it's essential for the second part because we're actually going to use this to enable us to shift statistical distributions and keep track of what the uncertainty is. One thing to note in here is that if the average of your distribution is 0, then this thing just becomes square root of x squared, square root of the average of x squared, which is sort of the definition that we mentioned earlier for root mean square, right? Basically what we take is the difference away from the 0 of the distribution, square it, take the average, and then take the square root. So earlier when I was talking about root mean square, really what I was doing was talking about standard deviation for a distribution that has been shifted back to 0 mean. And so if you're not at 0 mean, you just need to correct that root mean square for the fact that the mean is not 0 in that distribution. Okay, so root mean square, standard deviation are more or less exactly the same thing, as long as in the second half of this lecture we can show that the uncertainty or the standard deviation doesn't change, but when you take a distribution that's away from 0 and just slide it back to 0 in order to consider it. Okay. So just finishing off and referencing back to our uncertainty distribution, if we think in terms of expectation value now, for any particular variable we like, and it could be just x along a 1D line, then we can take some particle that's at some position out here, and we can say the position will be the expectation value, and the uncertainty in that position will basically be the standard deviation for the expectation value distribution that we have for the particular scenario that we're dealing with. Okay, and we can define that essentially as the square root of the difference between the average of L squared minus the square of the expectation value. Okay, and you can obtain this Here, in much the same way that you obtain this. So if you're looking at the expectation value, what you're basically taking is either the sum of the probabilities times the eigenvalues, or you can take, in bracket notation, just the ket and the bra for your particular state with the operator L in the middle. You can take more or less the similar approach for getting L squared, right? So you would have bra ket L squared in the middle and work that out. Or what you would do is take the probability weighted average of the square of the eigenvalue to get that distribution for this side. And that gives you an uncertainty that you can work with. So I'll take a break here, and in the second half, we'll come back and look at shifting distributions.